Hello class, greetings from Qatar, or at least that's where I will be on Monday and Wednesday when you're in class. So today we're starting chapter 7, which is mechanical properties. And some of this will be a review, I think, for many people, so we're going to go fairly quickly through today's part. And our learning objectives are as follows. First, we're going to review basic stress versus strain. We're going to talk about the difference between true stress and strain and engineering stress and strain. We're going to use Hooke's law to calculate the amount of strain that occurs in the elastic region for a given stress. We'll identify things like yield stress, proportional limit, ultimate tensile strength, toughness, and resilience from stress-strain curves. We will calculate Poisson's ratio and relate shear and Young's modulus via this Poisson's ratio. Finally, we'll calculate true stress and strain from the instantaneous stress and strain sample geometry, right? So let's recap where we've been. We've just finished learning about defects in solid. So now we're going to be able to relate these two mechanical properties, but first we need to talk about mechanical properties of pure metals, right? Not defected like alloys. We'll start with pure metals, right? So why do these matter? They matter because forces are applied to materials all around us all the time, right? They lead to accidents. They might be involved in the safety of materials if they fail intentionally at a certain stress as opposed to failing catastrophically in an uncontrolled way. And things deform all the time. They deform under loads, whether those are torsion, shear, compression. They deform all the time, and we need to be able to understand how materials deform when they're being used, okay? So some of the questions that we'll be able to answer, hopefully by the end of this chapter, is, just how strong are materials? How much can they deform? If they deform, is it going to be reversible? Well, what influences strong versus hard materials? What leads to one being one being the other? Why is it different, right? It's going to be necessary to test for strength, hardness, ductility, stiffness, lots of different things, but under a lot of different conditions, right? If you change the time that something's loaded, that can change it, right? Creep, for example. Creep, a few chapters ago, we said on the first day when you load it, you don't observe anything. But after a month or a year, all of a sudden it's deformed quite a bit. But the environment, like is it near the ocean? Will the humidity matter? What about, is it have lots of thermal temperature cycling? Will that affect things? Because all these things will in fact influence a lot of the properties we care about, we need ways to determine how to test properties, right? And there's actually whole organizations dedicated towards testing, mechanical and otherwise, right? And the way that we do so, we test things in a organized manner, is by following things like the ASTM. So what is the ASTM? Well, the ASTM stands for the American Society of Testing Materials, right? So what you can look at in here, it gives you all sorts of different ways to test different materials for different applications. Literally, you could pick anything you wanted in here. We could put like electrochromic, right? Something strange like the materials that we work on in my research group, these goggles, these ski goggles that can change their color. There are whole ASTM standards on how to test these things, right? If you make an electrochromic device and you seal it in an insulated glass, how do you do accelerated aging, right? So that you don't have to wait for it to cycle for 100 years to get all the cycles. You can accelerate that process. This will tell you exactly how to do it. Now the downside is it says you have to buy these PDFs, right? Technically these things you have to pay a subscription fee for it. Now the good news is that the university has all of these things. So if you go through the university library, they have a link that will get you all these things for free. But it will have a very detailed prescription on how to go about testing things. This is important because if I'm here in the United States and I test it one way, this allows somebody else on the whole other side of the world to test it the exact same way, so that when we publish it, we all are talking about the exact same thing. There's no ambiguity like, oh, well, how did you test it? These lay out the exact way that you should test things, okay? Which is really valuable. Okay, let's dive into the types of stresses that are going to appear on forces, right? So you've got tension, compression, and shear, right? So let's take a look at these. So tension, you have your sample and you're pulling on it, right? You're pulling this way and that way. But the key is that you're pulling orthogonal to the face of the material, right? So here's your face of your material. The load is perpendicular. It's straight up and straight down, okay? Now, compression is when it's down, when you're squeezing the material. Tension is when it's pulling it, obviously. When you pull on something, you can see that it gets longer, right? Here's your initial length, L0. L final is it got longer when you pulled on it. And conversely, when you squeeze on something, it gets shorter, right? So here's our initial length, and this was our initial length, this is our final, it got shorter. Now you'll notice in these drawings that this one also got fatter. Its radius increased, whereas this one got smaller, right? That has to do with something called Poisson's ratio, which we'll come back to in a minute. Now, instead of loading it perpendicular to the face of the material, you can load it parallel to the face of the material. So shear, in this case, you're smearing along the surfaces of the material. So literally, if you took like a phone and I push it along the surface, like if I'm loading it like that, it's perpendicular, right? But I could also shear it along that face, okay? So you can have different forces depending on how the direction is applied to your material. And the types of deformation you see are very different. Like take a look at shear. Instead of just getting longer or shorter, it's deforming the material, right? You're getting this deformation here where you can quantify the amount of strain with this angle. So that angle right there, we're going to call it, it's sometimes called gamma or theta, but it's an angle, right, at which you now have tilted your material, okay? And then if you fix one side of your material like that, and then you twist another, you can get torsion, right? So it's just a combination of stresses that we've seen before. This is still applying a shear stress along parallel to the face, but you're fixing one side, and so now this angle, right, it's fixed at one end, so it's going to start to twist, right? So it's a torsion, okay? Okay, there's lots of different types of tests for these different types of forces on a material. One of the most common is to do a uniaxial test, uniaxial strain. So we're going to pull on it just straight up and straight down. Now, when they do this, you almost always do it with a certain shape. We'll call this one right here, this is called a dog bone. This is also a dog bone test. Why do they do this with this specific shape? The reason that they have a specific shape is because you have to grab this thing somehow, right? You literally, your device for testing this, you guys have probably seen these before, but it has this cross beam here that can move up and down. It's got a plate here that you're going to attach your sample to, so it's got a clamp. This thing's got a clamp, and your sample goes here in the middle. So you've got your dog bone shaped sample. And when you clamp onto that thing on the top and bottom, I imagine just with a pencil, if I put some, like some vice grips on this thing, if I squeeze onto it, I'm going to be putting little dents in the pencil, and that allows me to grab onto it. So then when I start to pull it, it might break right where I grabbed onto it, because that's where the teeth of the pliers bit into it, and you don't want that. You don't want it to fail because of some defect when you grabbed it. That's not what you want. So instead, you want it to fail in a spot where it's just the pure material. So by designing it as a dog bone, think of what you're doing. So here's your shape. You're going to squeeze onto it up here, so you can grab onto this with pliers, right, the clamps in these regions, but it has a much smaller cross-sectional area in the middle. Well, think about what stress is. Stress is defined as the force divided by the cross-sectional area. So if you're applying the same force to this thing, then the stress in this region, we'll call this stress 1 right here, versus right here, we'll call that stress 2. Stress 2 is going to be greater than stress 1 because the area got smaller, right? Here's a big area, here's a small area. So because this is at a higher stress, it should fail here in the middle, and that's what you see. It fails here in this middle section, here in this middle gauge section. That's by design, so that you don't break from just grabbing it and damaging the material, but it breaks due to the pure material's properties and not how you're grabbing onto it, okay? So you've got your stress, which is the force over the area. Now notice here, I'm putting A naught. A naught means your original area. Same thing here, L naught is your initial area. Oops. L naught is your initial area, where Li is the instantaneous area. So at some moment in time, if you stop the experiment, it's how long it is, even though it was this long when it started, okay? So that's your stress and your strain. Strain, we talked about both of these at length in this class. Now these are engineering stress and strain because they account for the initial cross-sectional area and the initial length, okay? Okay. Now force units here is a common problem. Make sure that you're doing force in something like newtons, and if you have newtons and your area is in meters squared, then stress is newtons per meter squared. That is defined as, well, 1 Pascal, or in other words, a megapascal, which is a common unit of stress, is 1,000,000 of these newtons per meter squared, right? 1 megapascal is 1,000,000 pascals, so it's 1,000,000 of those. And then strain, look at strain. You've got change in length divided by length. So that's just length divided by length. So it has no units. It's just like percent, right? Percent has no units. It's a percent. Or ppm, parts per million, has no units. It's just a parts per million. It's 1 divided by 1,000,000. So that's strain. It doesn't have units. Okay, compressive tests. You don't need dog bone samples for these typically. You can just take cylinders, like a little battery shaped, and you just squeeze on it. If it has a flat surface, right? Imagine this. Let's say you've got a sample like this versus a sample that's actually shaped like a battery, which is like that. If you squeezed on these two things, so you've got a plate coming down on them, this one you're going to have a higher stress in this middle region there because it's a smaller cross-sectional area. Whereas this one, it'll be a nice uniform stress all the way through it, assuming that it's nice and planar when you squeeze on it. So if you were to squeeze this one, this part up here might be the first part to break, right? Because it has a higher stress depending on the material it's made of. Okay. These are a little bit less common, but they can be useful. Sometimes materials that are brittle are hard to do tensile tests on, and compression tests are a good alternative. Okay. Then you've got shear and torsional tests. We've already talked about those. It's the same. It's still a force over an area, but the force is being applied parallel to the plane as opposed to perpendicular. And we measure the strain, right? This is going to be the shear strain, gamma. Shear strain is going to be equal to the tangent divided by that angle theta, which is if you had your material after it's deformed from the vertical. Let's say it started out there. That's your angle theta after you stress it. So you're applying a stress this way and a stress that way. That's how we define shear strain. Okay. And what's interesting is that in a material, even though you think you're applying one thing, you can get a combination of different loads happening inside of it. What do I mean by that? Well, let's assume we start out with this nice material, right? A nice cylinder. In this cylinder, you apply a force directly straight up and straight down. It's perpendicular, right? Sometimes I'll put that little mark like that to show that it's perpendicular, okay? Well, at some plane within your material, arbitrarily defined, right? This plane that cuts through your material, imaginary plane if you want, this force that you're applying is now no longer perpendicular to that plane, right? It has a perpendicular component and it has a parallel component. So along that plane, you could figure out, okay, what is the stress versus the shear stress, right? The stress that you get, or the shear stress you get, it'll be a function of your initial stress, right? That's your initial one. It's this guy right there, right? The one that you're getting by looking at the cross-sectional area. But then it's going to depend on the angle, right? The angle of this plane, if that's theta, then you can figure out what it's actually doing. And along that plane, you might have a significant shear stress, right? The shear stress might be really large. So why do we care about that? The reason we care about that is because typically, many materials, they tend to slide past each other before they break from each other, right? The bonds between two atoms might be fairly strong, and breaking that bond might be challenging. But sliding things where the bond just has to reform with another one nearby, like if you've got a series of atoms, if they can just slide past one another, that can happen at a lower stress. So even though you think, oh, this thing should be plenty strong enough, the bonds won't break if I load this thing, you can still get deformation. You might get this happening. Right, where it slid past one another. That's a bad drawing, but I hope you get the point, what I'm trying to make here. This thing can slide due to the what we call the resolved shear stress on some imaginary plane in your material. What planes might those be? Well, they might be the exact sort of planes that we learned about in chapter 3 when we talked about planes going through crystal structures, right? The 110, the 111, the 010 plane. That's exactly what we're talking about here. That's why we learned about those, because they become useful. Okay? So we will talk more about that next chapter when we get to deformation mechanisms. So that's just a primer on that. Now let's get to elastic deformation. So there's elastic and there's plastic deformation. Elastic means it's reversible, right? If you stretch a rubber band, I don't have one here. Like if you stretch a rubber band, it will stretch a certain amount and then it will go back. Stretch a certain amount and then it goes back. And it's reversible. But if I stretch this too much, I might stretch it out and then it breaks. I transferred from elastic regime to a plastic regime, and that's possible. Okay? So how much strain do you get when you apply a load on something? I take this rubber band and I pull it and I get a certain amount of elongation. So how much elongation do I get? It's proportional to something called the Young's modulus, the stiffness, right? So in other words, stress is equal to strain multiplied by Young's modulus. So Young's modulus tells you how much deformation you get in a material. If you have a really stiff material, then you're going to have a different Young's modulus than a material that's really compliant. You're going to have a different Young's modulus, okay? Named after Thomas Young, by the way, who is a fascinating character, like an Egyptologist and all sorts of other things. Well worth reading his wiki page. Interesting guy. He's a polymath in that he basically looked at everything. He studied mechanics, but also light, sound, language, musical harmony, and Egyptology, which is pretty rad. Okay? Strain has the units that are unitless, right? Strain has no units. So modulus must have the same units as stress, right? Because stress equals strain times modulus, so it must have the same units, and it does. Megapascals typically, or gigapascals commonly. And if these things are proportional, then we call this, well, it's linear elastic, okay? So stress versus strain is linear for many materials, okay? Therefore, the modulus is the stiffness or the resistance to deformation, and it's non-permanent or it's reversible. So imagine this scenario, right? You've got this curve. This is stress on your y-axis, and you've got strain on your x-axis. This is a super common, what we call a stress versus strain curve. You've seen them before, and you have these different scenarios, right? So you can take the slope of this line, you can take the slope of that line, the slope of that line. In all of those, they're still linear. It's just what the slope is. That is your Young's modulus, right? Because stress equals strain times your Young's modulus, right? So it's the slope. It's the slope for that relationship when you plot y versus x. This is just the slope, okay? So we would say that for these materials, one has a high modulus, one has a medium, one has a low. So what materials might these be? Which one's the ceramic, which one's the polymer, and which one's the brittle steel, right? Well, ceramic is going to be the one that has the highest Young's modulus. Ceramics tend to be extremely stiff. They don't bend. Whereas a brittle steel also has a fairly high modulus. It's fairly stiff, but once it starts deforming, it just fractures. Meanwhile, a polymer is much more compliant. So it has a lower modulus, a lower slope. But when it starts to deviate from this linear regime, all of a sudden it starts doing these funny things over here. And it doesn't break until some much larger strain, whereas the steel broke at a relatively low strain, and the ceramic broke at almost zero strain. It doesn't tolerate any, like if you took a dinner plate and you start flexing it, it's not going to flex at all before it fractures. Whereas a metal, it might fracture a fair bit, and a polymer might. I mean, look at the rubber bandit. The elastomer stretched a bunch. That's like this black line down here at the bottom. That would be the rubber, or the elastomer. Elastomer and rubber are the same thing, okay? It stretches a whole bunch, and it's not linearly difficult, okay? So that is Young's modulus, okay? Now, you can have non-linear but elastic deformation. That is possible. Some materials, right? Cement, cast iron, polymers, right? Take this polymer. This thing is definitely elastic. It goes all the way back to its shape, but it's not linearly difficult. It changes the response to stiffness as we go. Right? It starts out being easy, and then it gets harder and harder. Okay? So that's possible. However, most materials, well, materials that are not brittle, they will start to deform, right? Now, a material like a ceramic that's brittle, instead of deforming, it will just fracture. But other materials will deform, okay? By the way, this ties into what we learned about previously, so a quick reminder. If we were to plot energy versus interatomic bonding, we got this potential energy well, and it did something like that. If instead of plotting, that was supposed to be energy, if instead we plotted force against distance, remember it looked like this. It had a maximum value and then went down. And we've been saying that if, see, this is your equilibrium distance, that's the equilibrium bond distance. The slope at that line, think about what that is. The slope of that line tells you how much force is required to spread your atoms out a little bit if you were to pull on it. So this should be proportional to Young's modulus, E. Sometimes we call it E sub Y, right? Right? At that point, that should be proportional to your stiffness, which is why we used that earlier this semester, right? Okay, so what are some typical values that you can expect for Young's modulus, or this elastic modulus? It's the same thing. So ceramics are typically something like 50 to 400 gigapascals. So gigapascal, that's a billion pascals, 1 times 10 to the ninth. For metals, it's going to be less, maybe a few hundred gigapascals down to the megapascal region. And for polymers, you can be something like 0.1, so 100 megapascals up to maybe 5 gigapascals, depending on your polymer. So ceramics tend to be the stiffest, polymers tend to be the most compliant, metals typically are in the middle, okay? Many materials get weaker, not weaker, they get more compliant. They become less stiff as you heat them up. This makes sense if you've ever made like caramel, right? Caramel, when it's cold, is very stiff. It's brittle. But when you warm it up, it becomes compliant, right? Caramel. So many materials behave that same way. When you heat them up, they increase their compliance. But not all materials. Like rubber actually goes the other way. It actually gets it actually becomes more stiff as you heat it up. And maybe you've experienced, if you ever took like a piece of rubber and you got it too hot, it actually starts cracking and becoming brittle because you're altering the chemicals in the structure inside of it, which we'll get to probably later. Okay, so we showed that for regular stress and regular strain that they were proportional. We said that the stress applied is going to be equal to the strain multiplied by the Young's modulus, okay? But the exact same relationship exists for shear stress and shear strain, right? The shear stress that you apply will produce a shear strain dependent on the shear modulus, right? So G is now our shear modulus. So it's just the constant of proportionality that tells you how much shear strain you get when you apply a shear stress, okay? Now, something that's really interesting is you can get anelasticity. Anelasticity is fascinating. What this is it's time-dependent elastic response. In other words, when you first apply the load, it's not immediate, it takes a minute, because there's microscopic or atomic processes that happen over a period of time, and it's slow. Now, for metals and ceramics, it's typically so low that it can be neglected, but it can be large in materials like polymers. You can see whole types of behavior which we call viscoelastic. It looks kind of like a mix between viscous and elastic. And there's actually some fascinating studies, like check this one out. This is a guy, I think at Georgia Tech, who's looking at
This
fire
brown
ants.
goopy material looks like mud, but it's alive. It's made of fire ants.
And you can see that
Solenopsis
as they
invicta. That's a
test
Latin
these
word
fire
for
ants in all sorts of different ways.
One of the few insects capable of building big structures with their.
They
Yeah,
will,
like water has these hydrogen bonds. It's
a drop
here.
of dye.
As they slowly start out with them pumped together,
In their
they will
study of the
slowly
towers
spread
that
out
fire
as
ants
they
build after
squeeze
floods,
on them
whose
and
team
test
found
them
that,
in different
which is
ways.
how they stay
These
afloat
things
during a
behave
flood.
as
they
a
link their bodies
viscoelastic
so
material,
closely
which is
together.
pretty
They
cool.
actually.
Okay. All right, the next thing we want to learn about is Poisson's ratio. And we showed this already, that if you start out with a material and let's say you pull it, its initial dimension right here, L, it's going to change. It's going to get elongated. But the radius, right, this radius of this will also change. It's going to shrink, right? Why does this happen? Because we're conserving matter, right? If the volume both got longer and got wider, it would increase its overall volume, and that's not typically something that can happen, okay? So, defined strictly, we'd say that if the deformation is happening in the z direction, right, that's where we're applying the load, is in the z direction. If it's being elongated there, it will constrict in the x and y directions. Or the way we've defined it here is length and radius. You can do it that way as well. Or if you're squeezing on it, right, then you're going to see growth in the x and y directions, okay? So what we define here is V. V is our Poisson's ratio. It's the ratio of lateral to axial strains, right? So it's going to be, we always put the negative sign in there so that it's a positive number. Negative strain in the x direction divided by the strain in the z direction, or negative strain in the y direction divided by the z direction, okay? And what can this value be? Well, for most materials, it lies between a quarter if it's an isotropic material, up to 1/2 if there's no volume change at all, okay? And then typical values are something like 0.25 to 0.35, but there are some extreme end members. For example, rubber is basically incompressible. So as you squeeze it, it just bulges out and you get the Poisson ratio of 0.5, basically. Whereas other materials like cork is compressible. If you squeeze it, it doesn't expand at all. It's almost zero because it has all these pores and air pockets inside of it that allow it to collapse onto themselves as you squeeze it, okay? what's interesting is that if you do have these this Poisson ratio for material, it allows us to relate Young's modulus to shear modulus for isotropic materials, right? Remind ourselves what isotropic means. Isotropic means that if you have your material, the properties that you measure, they don't depend on the direction that you apply them on your material, right? If you apply it on the 111 direction or the 100 or the 010, you get the same properties, right? That can be because your crystal itself is isotropic, but it's more commonly due to, if this is your material, it's made up of lots of little grains, and these are all randomly oriented, so that overall, it doesn't matter how you load this thing, it behaves the same way, okay? So this relationship holds for isotropic materials, where you can figure out your Young's modulus if you know the shear modulus. Or measuring Young's modulus is easy. You can get Poisson's ratio pretty easily, but measuring shear modulus is typically more challenging. This gives you a way to calculate it, okay? And we've got some examples worked out on YouTube for that. All right, so up until now, everything's been nice and elastic. You pull on something and then it will go back. What happens when you get plastic deformation? Well, this is permanent and non-reversible. That's the key words here, non-reversible and permanent. So Hooke's law no longer applies. Take a look at this. Here's your stress versus strain curve. You've got this region of the plot where it's nice and linear. You can load it all the way up from point 1 to point 2, and if you let go, it will go back to its origin. You have total reversibility, like our rubber band. Great example. Goes right back to the shape it was in, even though I'm loading it. But there exists the concept of yielding, right? Yielding is plastic deformation. And so you can have a yield strength. And technically, the yield happens right at about 3. You see at point 3 it transitions from a nice linear curve and it starts bending and becoming nonlinear. And at any of these points, if you were to take it back, if you were to unload it, it would retain this Young's modulus here, but there would be some permanent deformation, right? So when we talk about this, we as a field, we needed a way to define yield strength. What is the strength at which you transition from elastic to permanent deformation? That's a useful engineering concept to know. We'd like to know when will things start to yield. We decided as a community that we're going to accept this value right here. We'd call this sigma y. Sigma y corresponds to the point that when you unload it, it goes back down and you're left with 0.2% strain. Why on earth did it pick 0.2% strain? I have no idea. I didn't do it, so don't blame me. I think what they did is that it's small, but it's measurably small. You don't have to have a super precise instrument to figure out when you have 2% strain. So this is what they sort of decided on. They said that we'll define that as yield strength. As soon as you have 0.2% permanent deformation, it's starting to yield. And so you can define the stress at 0.4 at which that happens, okay? Sometimes it's nice and gradual, and sometimes you get really strange things, right? It's nice and linear for this material, but then it drops suddenly, and it does some weird stuff, and then it starts climbing again, right? So we call these yield point phenomenon when they do this, stuff like this, and it's fairly common. So what are some values you can expect? Typical values can be like 35 megapascals for aluminum, all the way up to 1.5 gigapascals for steel, right? So steel, it might not start to yield until a really high strength compared to something like aluminum, okay? Now, there's another term that you should be aware of. Oops. Right here, here's where it yielded, right? That would be your yield strength. But up here, we often call that UTS, which is your ultimate tensile strength. Sometimes they'll call it tensile strength, TS, or ultimate tensile strength. It's all the same thing. It's the point in the curve, it clearly started elastically deforming, but it still was taking a higher and higher load until some point, and then it takes a smaller and smaller load until it fractures. So it's a fair question. What do you think is happening? It seems to me you see it getting stronger all the way up through there. Even though it's deforming, it's still tolerating a higher and higher load, right? Up to some maximum stress. And then it starts to get weaker. So next chapter, we'll learn why things get harder as we load them. It has to do with something called strain hardening. which has to do with the dislocations moving in a material, and then they start running into each other, and then they can't move as easily, so it's getting harder. We'll talk about that next chapter. But why would that ever stop? It doesn't stop. Instead, what happens is it starts necking, right? So if this is your material, this is the dog bone before we bend it, before we pull on it. When we start to pull on this thing, let's say that this is where it's going to start to fail. What will happen is it's going to neck down. So this was our initial dog bone shape. I messed that up. Okay, so this was the initial gauge length right there in the middle. But in this region, you get necking. You get necking where it draws down and gets even smaller. So the cross-sectional area there is way smaller than what the original gauge length was. The original gauge length we could have calculated, right, over here. But now this region, that gauge length is even smaller. The problem with these plots as they're shown here is that this is stress, engineering stress, which is force over the instantaneous, or the original cross-sectional area. But the cross-sectional area is changing. It's changing here, right? So even though this looks like it's getting lower, that's just because we're assuming that it had the same cross-sectional area that it had when we started. And it doesn't. It's getting smaller. In fact, if you accounted for the change in the cross-sectional area, you'd see that it keeps getting stronger. That's the difference between engineering stress and true stress. Engineering strain and true strain, right? So true stress and true strain says it's not the force over the initial area, it's the force divided by the instantaneous area, hence the A sub I. Or the true strain, it's not just the change in length divided by the length, it's the natural log of the instantaneous length divided by your initial length. So where does that come from? It comes from the fact that strain is the difference in length divided by the initial length. So if you have instantaneously, if you take really, really small segments of that, you can turn it into a sum. You can integrate that. When you integrate dl over L, that's where the natural log of Li over L naught comes from. In any case, we have terms that we can use for calculating the true stress and the true strain in a material, which are more accurate to what's actually happening inside a material. But it's harder to measure because you have to have instantaneous measurements of both the length, which is easy, and the cross-sectional area, which is hard. That can be hard to do, to measure that. Okay? And then if you have a material where there's no volume change, if that's a fair assumption in your material, it's not like there's a bunch of pores that are collapsing or changing shape or something like that, then we have a nice way to go from true stress and true strain to engineering stress and engineering strain with those equations right there. Okay? Now these expressions are only valid up until necking occurs. When necking occurs, you have to modify it. And again, we already showed what the plot would look like. If you have a material that behaves, and you were going to plot true stress and true strain, instead of it getting to a maximum stress and then falling off, you'd see the following instead. You'd see that it goes, maybe it starts to deform, and then it just keeps on going until it fractures. Whereas the original engineering stress and strain makes it look like it's getting weaker, but that's just because it's necking down. It's getting thinner in some part of the plot. Okay? And you can see that. So here's your initial bar where they had markings on it. Let's assume that these are like 1 centimeter apart. Well, here you see that those are now way more than 1 centimeter apart. They've drawn down, so that's because necking occurred. Okay? That typically happens above your tensile stress, the ultimate tensile stress, because once it starts necking, it's going to support less and less load because the local stress is much, much higher. Okay? And you can look up typical values for those in the back of the book and elsewhere. Okay? Okay, a few more things before we end today. Let's talk about identify resilience and toughness on these curves. Okay, so first off, there's ductility. So the amount of plastic deformation up until fracture is what we call percent elongation or percent reduction in area. So it's literally, what is the final length? If you pull on something, it's getting longer and longer. What's the maximum length that it achieved? Minus the initial length, divide that by the initial. That's your percent elongation. That's a useful metric, right? You could look it up for steel. What's the percent elongation it achieves? Is it 5%? Is it 100%? Depends on what type of steel you're using, probably. Or you can think of it in terms of reduction of area, right? If the sample started out with that gauge length and you pulled on it until it got thinner and thinner and thinner, maybe this was its final gauge length right when it broke. So you could define ductility in either of those two ways, okay? And by the way, notice here, for area, it's initial minus final, not final minus initial. It's the opposite of length. That's not a typo. Okay, another thing is you've got these stress versus strain curves, right? You've got your stress, you've got your strain. What about the area under the curve? What is the area under the curve equal to in mathematics? It's the product of your two axes. So here it's going to be the product of stress times strain, and it's equal to the amount of energy that gets absorbed during deformation. And take a look at this, the brittle versus ductile material. If you remember a couple chapters ago when we looked at failure and we did that Sharpie impact test, right? If we go back to failure, right here, and we basically said using this tool we could break our material. So we go all the way through elastic and plastic deformation all the way to fracture, and we could look at the energy absorbed during that process. And basically we saw this transition from a ductile material out here which absorbs lots of energy to a brittle material which doesn't absorb very much energy. This is that energy that we're talking about. It's that area under the curve, right? So you can have a material that absorbs lots of energy, and that would be this blue curve. You'd want a ductile material for that. Whereas a brittle material is not going to absorb much area under the curve during its fracture. Okay? So what are the units of this? Well, we just said that it's the product of the axes. So it's stress multiplied by the strain, right? And if it's a nice easy shape like this one, this red one kind of looks like a triangle. So the red one you could just do maybe 1/2 base times height equals, 1/2 the base, which would be your strain, multiplied by your maximum stress. That would be a good approximation for the strain, or for the toughness, excuse me. But the blue one, you can't do that. So maybe you could think of other ways to do it. Maybe you could call this one roughly a square, add that to the triangle, and you could do it that way geometrically. But really the best way to do this is to do it numerically. Basically take a tiny instantaneous point to do numerical integration. Each one of these, assume it's a little column. If you don't remember how to do numerical integration, it's worth looking up again. Okay? And what would the units be, right? So it's going to be pascals, right? Because we just said that it's stress times strain, which is just going to have the units of, let's say, megapascals. So how is that an energy? Well, remember that a pascal is a Newton per meter squared. And then what's a Newton? Well, that's equal to a joule per Newton. Or, sorry, a Newton is equal to a joule per meter. So a Newton per meter squared is equal to a joule per meter cubed. So for some volume of your material, that's the meter cubed, it's some energy is stored in that material when you fracture it, right? Which is pretty cool. It tells you the amount of energy in that fracture. Okay, one last thing we should talk about is resilience. The difference between toughness, which is this area under the total curve, that's toughness. Resilience is just the area under the elastic portion. So for example, take the blue curve. If we were doing the blue curve for a minute, if we stopped right here and we took this area under that blue curve, that would be the resilience, meaning it's how much energy can be absorbed without permanently deforming it. That's a useful thing, like springs. For springs, you want a spring to be able to go back and forth like this. This thing, you want lots of energy maybe if you want a stiff rubber band, but you don't want it to deform, so you want a high resilience. So that's the difference between toughness, which is the total area, meaning this is all permanently deformed in this region, versus non-deformed permanent, not just elastic deformation, not plastic deformation. Okay, and we'll pick up here next class.